Hello everyone. Welcome to this webinar on exploiting Copernicus data with ILWIS-4. This webinar is brought to you by the ITC Faculty of Geoinformation Science and Earth Observation of the University of Twente and is part of the 52 North GI Innovation webinar series. My name is Rob Lemmens. I'm Assistant Professor at ITC and Project Leader of ILWIS. This webinar is about Copernicus satellite data and the latest version of ILWIS, version 4, which is developed at ITC. Please note that this is not the beta version yet, but an alpha version, so some of the functionality that you might expect is not implemented yet. As many of you know, ITC carries out research and capacity development in geoinformation science and Earth observation technology. We develop training for a wide variety of applications and make intensive use of satellite-based sensors and their derived data. It is therefore no surprise that we look closely at the latest developments around the ESA Copernicus program. This is the world's largest single Earth observation program directed by the European Commission in partnership with the European Space Agency, ESA, previously known as the Global Monitoring of Environment and Security, GMES. Under the Copernicus program, a wide variety of data is acquired through the different satellite missions, called Sentinels. Pre-processed data is made available for free through services, but we can also access the raw data. There is a limited number of software packages available to process the raw data. In this webinar, we will focus on two of them. The Sentinel application platform, SNAP, is a dedicated toolbox made available by ESA for Copernicus data. The second is our own software, ILWIS, which is a software that we develop in-house. Now, ILWIS stands for Integrated Land and Water Information System. It's a PC-based integrated geographical information system and remote sensing software. ILWIS was originally designed in 1985 for a land use zoning and watershed management project in Sumatra, and it has been used extensively in courses, research and projects. In the screenshots you will see one of the earlier versions of the software. In 2007 we opened up the software and joined 52 North to develop the software further as open source. 52 North is a private research organization. Its R&D network is open to partners for research, industry and public administration. 52 North develops new concepts and technologies for spatial information infrastructures, providing a collaboration platform for open source software development. The most recent change is that we are using a modern architecture to support the wider spectrum of users and developers. This is called ILWIS-4. ILWIS has been used in many projects in which new software components have been developed and made available for further use in other projects and research. These components are used in the Windows desktop environment and in web applications, such as carrying capacity calculations for rangelands in Kenya, as you see in this picture, and for multi-spatial criteria evaluations on the web. In this way, ILWIS components can be connected to other software packages. This means that we can use the best software for each specific purpose. In this webinar, we will focus on the processing of Copernicus data through the desktop software functionality of SNAP and ILWIS. We will present this now in a brief manner, but you will get a link to the step-by-step guide later. I will now show you the basic functions of ILWIS Desktop. At startup, ILWIS opens your default data folder. You will see a fairly empty screen with the workbench on the left, in which you can find entries for data, operations, system messages, and more. For example, the locator allows you to manage your data folders. Operations will show you the operations which you can apply to raster and vector data. We'll see some other parts of the workbench later on. At the bottom of the screen, you'll find the contextual menu with actions and filters which can be applied to selected data and other objects. The workspace in the middle of the screen will display maps, graphs, tables, etc. Data can be explored in different ways. Each data item is represented by an icon which tells us whether it is a raster data, vector data, a coordinate system, etc. The thumbnail view shows us previews for each easy recognition and selection. We will now open the data container, which holds 8 of the 13 multispectral bands of Sentinel-2, and we'll open one of the bands in the map window. The image shows the city of Enschede and corresponds to the band 2 with a 0.49 micrometer wavelength. Common functions such as zoom and pan can be used to explore the image. Extra image information is provided by Pixel tool. The spectral reflectances will show at the cursor together with pixel coordinates in different coordinate systems at the top of the map. Let's now look at the display options of this satellite image. Just select Layer Specific under Data Attributes. There are several visual properties to inspect and change, such as Layer Info. This provides us information about the file location and coordinate system. Opacity. We can change the transparency of the image in case we need to see this layer together with another layer. And stretch limits. Here the histogram of the image will be computed and it will be shown on the right side of the window. You can improve the contrast by moving the sliders below the histogram or by selecting one of the stretching presets available, 0, 1, 2 or 5% of stretching. Let's go to another interesting function of ILWIS. All the bands of a multi-band raster can be visualized simultaneously in a synchronized view. This function can be useful in analyzing spectral differences of objects of interest. In the data panel, where the image is displayed, we can click the Split Panel tool, and we drag 3 other bands from the catalog in each of the empty subpanels. You can use bands 3, 4 and 8 for instance. The blue frame represents the selected image on which we can perform display actions, such as zoom, pan and inspect. Notice the clear contrast between the 3 visual bands, bands 2, 3 and 4, and band number 8, the near infrared, in the lower right subpanel. It is quite obvious that the vegetation areas on the western side of the canal are seen in a different way. With Sentinel-2 bands, you can create an RGB image in the form of a true or false color composite. In this case, a true color composite can be created by using the bands 4, 3 and 2, corresponding to the red, green and blue bands of the Sentinel-2 image. We do this by selecting the 3 bands in that order while holding the control button pressed. The selected bands will be displayed at the bottom. We click Apply and the map will show in the map window. Check out the red roof of the FC Twente soccer stadium. Finally, a false color composite is used to enhance vegetation in the image. It can be made by bands number 8, 4 and 3. In the last basic function that I will show to you, we are going to overlay some vector data on our color composite. You can perform this overlay as long as the layers have a defined georeference. To do this, drag the map called roads in the data panel containing the color composite and zoom in at different locations to check the overlay. You have now been introduced to the very basics of ILWIS. In our effort to make ILWIS also an educational software, first we emphasize the use of interactive tools and use drag and drop for data and operations. And second, by providing alternatives for processing through the use of menus, visual workflows and Python scripting. Some of these functions will now be demonstrated by Diana Chavarro Rincon.
Hello, my name is Diana. I am a member of the ILWIS team at ITC. In this webinar, I'll be guiding you through the processing steps of Copernicus data with Snap and IRWIS. In this section, I'm going to show you the pre-processing of the Sentinel-2 data in Snap, the Sentinel application platform. Snap is an open source package specially designed to process Sentinel images, but also images from other satellite missions. Snap can be downloaded from the Scientific Toolbox exploitation platform. Before doing the actual pre-processing, I'll show you how to download images from the Copernicus Open Access Hub. Go to the online interface. To get access to the data, you need to have an account. If you don't have one, you can create it by clicking on Sign Up. Fill in the required information and click on Register. When your account is activated, you can log in and start your search. Before selecting your area of interest, go to the Search menu. Fill in the fields according to your preferences to visualize the results. Select the sensing period. Click the Sentinel-2 mission box. You can make choices on satellite platform, relative orbit number, and product type if you have any preference, or you can leave the fields empty. In cloud cover, use up to 5% for an initial search. Navigate to your area of interest and mark it drawing a rectangle. When you're ready, click on the search icon. Have a look at the results of your search and the footprint of the images. You can have a preview of any image by clicking on the eye icon. In the preview, you will find useful information, including the actual cloud coverage. You can download the image from the review or from the results panel. Select a folder to store the image and download it. Note that you will download a zip file. To open the image in Snap, you can directly drag the zip file into the Product Explorer. You can also use the Open icon and the Unzipped folder. Open the product and check the metadata and band folders. Right-click on the product to open an RGB image. Use the default combination. That will give you a true color composite. Sentinel-2 images cover an area of 100 by 100 kilometers. You may need to subset it to your area of interest. But before doing that, you need to resample all the bands to the same spatial resolution. Sentinel-2 images come with bands at 60, 20, and 10 meter resolution. You can, for instance, resample all the bands to 10 meters. To do that, select the product and go to Raster, Geometric Operations, Resample. Make sure that the right product is selected in Source Product and check the output name. You don't need to save the file. Click on the Resampling Parameters tab, select B2, and leave the other parameters as default. Click on Run. The resample image will appear on the Product Explorer. Now select the new product and click on Raster, Subset. In the Subset menu, you can type either image or geographical coordinates to mark your area of interest, or you can manually adjust the blue rectangle. In the Band Subset tab, you can also select which bands to leave or subset. When you are ready, click on OK. The subset will be added to the Product Explorer. Open the subset as an RGB image, and if you are satisfied, save it. For that, right-click on the new product, select Save Product As, and navigate to the desired folder. The image is saved in DIM format by default. Finally, go to File, Export, GeoTIFF, and select a folder to export the new image. Now you are ready to work in ILWIS. In this section, I'll show you some of the ILWIS tools useful to obtain relevant information from satellite imagery. One of them is the spectral tool. With this tool, you can build a plot of the pixel value from multispectral images, for instance, spectral reflectances. We can get some insight into the nature of features by comparing these plots with typical spectral curves. To demonstrate the usefulness of this tool, I will use a multitemporal Sentinel-2 dataset of the Guadalquivir marshes in southern Spain. This is a natural region of marshy lowlands near the city of Sevilla, an area of extensive agriculture mainly dedicated to the cultivation of rice. But we can also find other crops such as wheat, cotton, tomatoes, etc. Multitemporal imagery at high spatial resolution, like the one obtained from Sentinel-2, provides reliable information to support agriculture monitoring, as we will see in this example. For the exercise, we will use a dataset of 8 Sentinel-2 images corresponding to the months of June to November of 2017 and January to May of 2018 to cover a full agricultural year. The pre-processing of the Sentinel-2 images was made in Snap, as explained in the previous section. The images with the spectral reflectances were exported to ILWIS in GeoTIFF format. Every image is represented in ILWIS as a multi-raster container. You can have a look at the content of the map by clicking on the icon. Here you can see the bands and the georeferences. Note that there are 2 versions of the image of June. The first includes all the original 12 bands of the sensor, as you can see. The second version, together with the other 7 images, have been subset to the first 8 bands to reduce the size, because we don't need the other 4 bands. Every image has been renamed, you can see in the list, adding the prefix SP 1 to 8 according to the acquisition order, and the suffix sub at the end to indicate that they were subset. We can open the 12 bands image as a color composite. For instance, a true color composite. For Sentinel-2, select bands 4, 3, and 2 for the RGB channels. 4, 3, and 2. Go to Actions for Selection and click on Apply to create the image. Okay, now we have our color composite. In the central part of the image, you will see the Guadalquivir River running north to south. The city of Sevilla would be in the northern part. Here we have the rice and the agricultural fields. There are some not cultivated plots, some bare soil, and also some buildings and villages nearby. To build a spectral plot, click on Layer Specific Cross-Section. In Data Source, drag the container. So we have to go 1 level up. Drag the container to the field and make sure that the 12 bands are included in the bands list. Select Continuous Mode and click anywhere on the image. The spectral plot will appear on the left panel. Here you can see the spectral plot for the selected pixel. Walk through the image to see the spectral signatures of different pixels. Like water, for instance, the rice plots. You can see different pixels. You can modify the aspect of the plot by selecting one of the operations. For instance, you can fix and lock the y-axis for a better visualization. I can fix it on the 10,000, for instance. Now you can see that it's easier to compare signatures. Let's zoom in into the agricultural area and click on different parcels. Note the changes in the plot. For different crops. We can also fix spectral curves of specific targets as a reference by adding pins. I will add a pin, for instance, in the river for water, in the paddies. I can also add in the other crops, in bare soil, in a building, for instance. Yeah. Now the 5 characteristics curves. Yeah, I can work a little bit on the aspect of the plots. I can change the color, for instance, for a more intuitive representation. Know the differences among spectral curves for my 5 pins. So I have here, for instance, for a bare soil and for the building, for the vegetation. Click on Continuous Mode and walk throughout the image to check the similarities of selected pixels with the reference curves. Yeah, you can see. Let's zoom in again in the cultivated area. Pixels in this area follow similar trend in the spectral curve, but not identical values. We can also obtain useful information calculating radiometric indices. You can do this in different ways in ILWIS. Let's do it initially using the mapcalc function, a raster calculator that can be used to perform simple or complex mathematical operations to generate thematic maps. For this exercise, we can build, for instance, NDVI maps. As you may know, the NDVI is obtained from this expression using the near-infrared and red bands, which for Sentinel-2 correspond to bands 8 and 4. Let's open the mapcal function, go to Operations and type map in the first field. We will use the mapcal2 as we will use 2 rasters. This. Go into the multi-raster container of the subset images, the first for instance, and drag bands 4 and 8 to the corresponding fields. Yeah. Type the NDVI expression, keeping in mind the order of the maps. Give a name to the output map, and in output format, select GeoTIFF. Finally, click on Execute and check the progress slider. You will find the NDVI map outside the container. Let's open it. Okay, yeah, we have it here. We can examine some of the pixel values. They should be negative for water and positive for the cultivated plots. Let's zoom in into the agricultural land. We will find mainly negative values for the rice fields, as they may be flooded at the time of the image. Yep. Okay, in the same way, you can calculate the NDVI maps for the other 7 images. I have already done it, so I have here my 8 NDVI maps from the multi-temporal dataset. Let's see how they look like. For that, we can use the split panel option to have a synchronized view of some of the maps. Drag some of them into the 4 panels, sorry. Click on one as a reference, zoom in and navigate throughout the image. You will see differences according to the time of the year. If you want to build a temporal plot, you need first to put the maps into a raster container. For that, go to Create and select Raster Coverage. Give a meaningful name. Select any of the georeferences. They are all the same. And drag all the maps into the bands box. Yeah, we will add it one by one. Good. Yeah. Okay. When you are ready, click on Apply and allow a few seconds to get the container built. Yeah. You can click on Operations again to close the workbench. So we'll have a little bit more space. So click on, yeah, okay. You will see the multi-raster container in the catalog. To build a plot, go to Layer Specific Cross-Section and drag the container in Data Source again. Check the bands, click on Continuous Mode, and click anywhere on the image. The plot shows the annual variability of the NDVI for select pixels. Check the variability for different features in the maps. zoom in again in the agricultural land, you can visualize different trends in the cultivated area. These differences are mainly related to the agricultural schedule of different crops. Another way to do the NDVI maps is using the Workflow Builder. With this tool, you can build chains of operations in a visual way. I will now show you how the NDVI calculation is built. From the workbench, we will create a workflow object and drag our operations on the workflow canvas. We start with the connections to our input data, the near-infrared band and the red band, 8 and 4. We drag the data icons into the input fields at the bottom menu, and we fill in the corresponding names. Then, we will add a map calc operation to calculate the first part of the formula, subtracting the red band from the near-infrared band. We connect both data layers with the map calc box and enter the subtraction into the expression field. We completed NDVI calculation with an addition and division operation. Now I have to click the play button at the top to run the workflow. The current running operation will highlight in red. Once finished, we can open the resulting map. This is the same map as we would obtain from a manual procedure as I showed before. You could also do it with a Python script. In the last section of our webinar, I'll show you a demo on how to integrate Copernicus data with other missions, for instance, Landsat. I will use as an example change detection in the Lake Urmia. This lake, located in a mountainous region in northwest Iran, is one of the country's most important ecosystems. It used to be a paradise for birds and tourists. Until the late 90s, the lake was well preserved, as you can see from satellite imagery. At its greatest extent, Lake Urmia was the largest lake in the Middle East. Unfortunately, due to climate change and man intervention, the lake has shrunk to 10% of its original size in the last 20 years. To monitor the changes, we will use a dataset of Landsat and Sentinel images to cover the period 2000-2018. So I have 3 Landsat 5 images from 2000, 2005, and 2010, 1 Landsat 8 from 2014, and 3 Sentinel-2 images from 2016, 17, and 18. The images were preprocessed in Snap and exported to ILWIS as GeoTIFF files. You can see here the dataset in the catalog. I have created some true color composites for visualization of the images of, I have for instance here 2000 and 2005, 2014, and the recent 2018. Here the whole dataset in which you can see the changes in water surface. They are evident. You can also notice a slight recovery of the lake between 2014 and 2016, which corresponds to some efforts of the Iranian government to rescue the lake. Unfortunately, its current situation is precarious. We could map these changes using, for instance, the normalized differential water index, which is obtained from the combination of the green and near-infrared bands. For that, we can use the map calc function of ILWIS in a similar way that we calculated before the vegetation index. I'm doing it here for the image of 2014 as an example. So I go to container, later I go to operation, map calc 2 again, but this time I select the green and the near-infrared bands. I type the expression, give a name, select the format, and okay. Here we have the map. Let's have a look at the resulting map. We should get positive values for water and negative for any other feature in the image. I have created here all the other maps. You can see some of them in the synchronized view. And as we, on the 2018, you can see the changes. As I can put it all together here. You can see the variation during the time of the study. Based on these maps, we can create a water mask to separate only pixels containing water. We can do that by applying a threshold to the water index. As an initial approach, I can say that pixels with positive values correspond to water. We can enter this condition in our map calculator in this way. map. And now I will select map 1 because I only need one map. Then I'll give the condition and calculate the map. Okay, here, execute, and the resulting map will show a pixel value of 1 for water, pixels with water, and 0 for anything else. So I have created here the masks, sorry. I have some of them here, and I can show you all the variation on the lake. Okay, so this was an example on how to combine Copernicus data with other satellite missions.
This brings us at the end of the webinar. Thank you for watching. We will now enter our Q&A session for your further questions. Please provide them in the questions section. Note that you can also take part in the polls that we have prepared in the polls section. Please remember that this is an alpha version of the software, and we are currently working on the documentation on the ILWIS website. We would like to have your feedback for improvements. We will send you a link to download the software and a step-by-step guide of what we have presented in this webinar. Now let's move to the Q&A.